Neural network is the heart of deep learning. The application of neural networks are everywhere nowadays. The way your phone can recognize your face or types messages hearing your voice, everything has neural networks behind them. Where is the concept of neural network came from? It is actually inspired by the learning process of human brains. Though it is not as sophisticated as human brain yet, but in some areas like image recognition, neural networks perform with far better accuracy than human eyes. Just imagine you see the pictures of all these people today. How many of them you will remember after a few days, or few weeks, or even few months? Hardly any, right? But once you train a neural network to learn these faces, it will always remember them. Let's get into a little deeper. And for that, I'm going to take a simpler image, like the picture of the digit 4. So how our brain learns that this is a picture of digit 4. And then once you learned it, then when you see this shape, which is a little different than the previous one, you know that this is a digit 4. When you see a different orientation, you still know that this is the digit 4. And then when you see these pictures with different background, we still know that this is a digit 4. How our brain learned it? We don't know because we can't see the working process of the neurons in our brain, right? But let's see what a computer can see when you give it a 28 by 28 pixel pictures of digit 4. It sees these numbers. This is 28 by 28 pixels two-dimensional array. When you are giving your machine the picture of a 28 by 28 pixels digit 4, you are actually giving these numbers to the machine. And now you are asking your machine that I'm giving you these numbers. Now you tell me, what is this? How your machine will know that all these numbers, they actually represent the digit 4. And then whenever you give your machine a picture of digit 4 with different shape, orientation, background, whatever it is, your machine should know that this is the digit 4. But how do you train your machine for that? The process will be almost like the human. Like when a little baby is born that doesn't know anything about this world, or it learns everything from the surroundings. And when the baby learns to read and write, somebody has to teach them. So we will take the machine or the model as a little baby, and we will take the baby steps to teach the machine the digits or whatever we want it to learn. Before we get to the training process of the neural network, I should remind you of the linear regression model, the most basic machine learning model that uses this linear formula y equals to ax plus b, where a is the slope and b is the intercept. When we adapt this formula for machine learning, we use y equals to wx plus b. So this w means weight and b means bias. And training this machine learning model means to find the right weight and bias so that the straight line fit the data correctly, the way it shows here. And when we have multiple input features, it becomes W1 x1 plus W2 x2 plus W3 x2 and so on, and bias at the end. We can use exactly same simple linear formula to train the neural network as well. So here is one very simple neural network where we have 3 input features, one hidden layer including 4 neurons. You can see this 4 round shape. It means 4 neurons. And then finally the output layer, and where we have 2 output. The learning process actually happens here in these 4 neurons. So this is the brain of the neural network. And here I'm showing only one hidden layer. A neural network can have multiple hidden layers. If you can understand how one hidden layer works, you will understand how multiple hidden layers work as well, because the working process is the same. Let's have an overview of how neural network actually works. The neural network includes a forward pass and a backpropagation, where forward pass calculates the output from the input. The next step is to check if the output matches with the true label. For example, we know the original output is 4. So we need to check if the output we calculated, if that is actually 4. If it's not 4, If it comes out to be 1, 7, 8, or anything else, that means there is an error. Then backpropagation calculates the necessary adjustments to the weights and biases to minimize that error. Here we will get into the detailed calculation of the neural network, how we do the forward pass and then the backpropagation. So let's talk about the forward pass first. From this input, we need to calculate these hidden layer values. And from these hidden layer values, the output. And don't worry, the mathematics behind it is actually simple. It follows this linear equation, y equals to ax plus b. So first start with how we calculate the values of this hidden layer from this input. Just notice x1, x2, and x3, all of them are connected to the A1, this top neuron of the hidden layer. And again, x1, x2, and x3, all three of them are connected to A2. Same way they all are connected to A3 and A4 as well. First, let's imagine we have only one input, x1, and only one neuron in the hidden layer, that is A1. How the connection between x1 and A1 works. This is the formula for that. So we need to initiate a weight, W11, multiply it by x1, and add the bias term, B11 here. See, it's exactly the same as the linear equation. Now consider x1, x2, x3, all of them, and see how it works. A1 becomes W11 times x1, W12 times x2, plus W13 times x3, plus B11. So we have to initiate these three weights, multiply with x1, x2, and x3, and then add B11, the bias term. And we do the same with A2. We have to initiate three other weights, W21 times x1 plus W22 times x2 plus W23 times x3 plus B12. And the same way you can calculate A3 and A4 as well. So this part is done. Now from hidden layer to output layer. And it's exactly the same process. All four of them, A1, A2, A3, and A4, are connected to H1, the first output. And again, A1, A2, A3, and A4, all of them are connected to H2 as well. This time, we need to initiate four weights to multiply with A1, A2, A3, and A4, and then add B21 to get H1. And the same way, H2 would be another four weights times A1, A2, A3, and A4 plus B22. So this weights and this hidden layer multiplication is actually the matrix multiplication. And then we have to add the bias. And in the same way, this input times these sets of weight is also another matrix multiplication. And we added the B1. In short, if we just simplify and call all this input x1, x2, x3 as x, and we can call a1, a2, a3, and a4 as a. Now, how we initialize the weights and biases? We can initialize them as something like this. Some values, random values from 0 to 1. That works. You can initialize all as zeros. You can initialize them as any other values like 0.5, 0.2, 0.25. Generally, I always initiate them as random values from 0 to 1. Now, if we simplify this whole thing, like if I call input x1, x2, and x3 as x, and then if I call a1, a2, a3, and a4 as a, the formula can look like this. A equals to w1x. So all the weights that we initiated for the first layer, for the input layer, I'm calling them as w1, and all the biases as b1. This is what the formula can look like, the simplified version. In the same way, if I call h1 and h2 the output as h, then it becomes like this, w2 times a is the hidden layer neurons, plus b2. W2 is all the weights that was initialized to multiply with A1, A2, A3, and A4, and B2 is all the biases. Well, this part is done. Look, this is the all linear formula, right? But it is important that we add some non-linearity to the model because the relationship is not always linear, right? To add some non-linearity to the model, it is important to pass the data to an activation function. Some commonly used activation functions are ReLU, tanh, and sigma. The ReLU activation function is this one. It returns 0 if your data is negative, but it's positive if it stays as it is. This is the formula for tan h activation function, e to the power x minus e to the power negative x over e to the power x plus e to the power negative x. And the sigmoid function, it squishes the data between 0 and 1. This one is very important for classification problem. Usually it is used right before the output. That means on the last hidden layer. So the output is between 0 and 1. Here I'm adding radio activation function on calculating A, the hidden layer neurons, and the sigmoid activation function to calculate the output. That's all about the forward pass. Then what? So we calculated this output, but do you think this output will match the original output or the true label? Possibility is not high at all, right? Because we initialized these weights and biases randomly, and then we calculate the output with some random numbers. So the output cannot really be close to the original output, right? So the whole work of the neural network algorithm is to refine these weights and biases. So these calculated outputs comes as close as possible to the original output. The first step is to check how far the calculated outputs are from the original outputs. For this demonstration, let's say we will use this one, this function, which is JW equals to original output Y minus the calculated output H. And we have to take the square of it so that the negatives do not cancel out the positives. Okay, and this JW is called as cost function. You will hear this term cost function when we'll talk about the backpropagation as well. Using this cost function, we will then backpropagate to improve our weights and biases so that our cost function JW is as less as possible. Now let's see how backpropagation actually works. So to update the weights and biases, first we need to know the differences. The difference in output, the original output and the calculated output, and then the differences in neurons, the value of these neurons and the original neurons that should be. The differences in outputs are easy because we know the original output because that should be given. It's a simple deduction operation like this. D3 equals to y minus h. Y is the original output and h is the output that we calculated. But the tricky part is the differences in these neurons because in these hidden layer neurons, we don't know the original value, right? So we need to go through some mathematical process for this. And we need the cost function that we discussed just a few minutes ago. So the cost function JW equals to y, the original output, minus h, the calculated output, squared. You have to take the partial differentiation of this cost function with respect to the weight times D3, the D3 that we just calculated using this y minus h formula, and times W2. The W2 is the weight that you used to calculate the output. If you perform this partial differentiation, this gets simplified to a times 1 minus a. So D2 becomes W2 times D3 times A times 1 minus A. So that's pretty much the backpropagation. You can use this D3 and D2 to update the weights and biases. So our new weights, W1, should be W1 minus X times D2 times learning rate. We'll talk about learning rate a little bit later. And W2 equals to W2 minus A. A is the neurons, hidden neurons, times D3, the D3 that we calculated, times learning rate. In the same way, you can update the bias terms B1 and B2 as well. Learning rate decides how fast or how slow you will approach to the optimum weights and biases. If you plot weights and loss, the graph shape should ideally look something close to this shape, and your optimum weight should lie in the bottom like this. And the losses should approach slowly to the optimum wherever it is. If we are not careful about choosing a right learning rate, it can keep overshooting like this one. Instead of going to the optimum, it can keep overshooting like this. Algorithm may never converge to the optimum weights. So it is very important to find a right learning rate, and it may take some trial and error. In my experience, I used learning rates of 0.01, 0.03, 0.001, or as low as 0.0001. And it may require 10, 20, 50, 100, 200, 300, or even 500 iterations or epochs of forward pass and back propagation to reach this optimum level. As I mentioned at the beginning, you can use multiple hidden layers, and the working process will be exactly the same. To improve the performance of your neural network, these are the things you can tweak. The number of hidden layers. It can be 1, 2, 3, 4, 5, 6, 7. So please try tweaking the number of hidden layers. Then the number of neurons in each hidden layer. Then activation functions. I showed a ReLU here. You can use other activation functions. We'll talk about more activation functions in future videos. The learning rate. It is very important to choose the right learning rate. Then the number of epochs. As I mentioned, it can be 10, 20, 50, 100, 200, 500. And if nothing works, you can also try initiating a different set of weights and biases. Even as a beginner, you have all these parameters or hyperparameters to play with to improve the performance of your neural network. There are actually a lot more that can be done to improve the performance of a neural network, but we will get there slowly. I'll stop here for today. I hope this video was useful for you. Please like, comment, share, and subscribe. Thank you so much for watching.